Let's go to the topic on the acetyl coenzyme A function. Acetyl coenzyme A is a central metabolic intermediate. The abundance of acetyl CoA in distinct subcellular compartments reflects the general energetic state of the cell. Moreover, acetyl CoA concentrations influence the activity or specificity of multiple enzymes, either in an allosteric manner or by altering substrate availability. Finally, by influencing the acetylation profile of several proteins, including histones, acetyl CoA controls key cellular processes, including energy metabolism, meiosis, and autophagy, both directly and via the epigenetic regulation of gene expression. Thus, acetyl CoA determines the balance between cellular catabolisms and anabolisms by simultaneously operating as a metabolic intermediate and as a second messenger. Let's go to the first part. Acetyl CoA acts as a central metabolite. Acetyl CoA is not only the product of multiple catabolic reactions, but also one of the central substrates for anabolic metabolism. For illustrative purpose, we will discuss the mitochondrial and extra-mitochondrial metabolisms of acetyl CoA separately. So let's go to focus on the generation of mitochondrial acetyl CoA. In most mammalian cells, acetyl CoA is predominantly generated in the mitochondrial matrix by various metabolic circuitries, namely glycolysis, beta oxidation, and the catabolisms of branched amino acids as shown in figure. Glycolysis culminates in the generation of cytosolic pyruvate, which is imported into mitochondria by the mitochondrial pyruvate carrier MPC. That is a heterodimer of MPC1 and MPC2. Mitochondrial pyruvate is decarboxylated to form acetyl CoA NDH by the so-called pyruvate dehydrogenase complex (PDC). PDC is a large multi-component system that in humans is composed of 3 proteins that are directly involved in CoA and ND-dependent pyruvate decarboxylation. 2 regulator components, for example, pyruvate dehydrogenase kinase and pyruvate dehydrogenase phosphatase. 1 non-enzymatic substrate, for example, pyruvate dehydrogenase complex 10. Alternatively, acetyl CoA can be generated as an product of beta oxidation. In this case, one among several members of the acetyl CoA synthase protein family catalyzes the CoA and ATP-dependent conversion of cytosolic-free fatty acid into acetyl CoA. Acetyl CoA is then condensed with L-carnitine to form acetylcarnitine and free CoA, a cytosolic reaction catalyzed by carnitine peptotransferase 1 (CPT1). Acetylcarnitine is imported into mitochondria through another solute carrier family 25 that is a member of 20 named SLC 25A20 with exchanged for free L-carnitine. Finally, mitochondrial acetylcarnitine is reverted by carnitine peptomatrix 2 (CPT2) into L-carnitine and acetyl CoA, and later undergo beta oxidation to generate NDH and acetyl CoA for use as direct and indirect, respectively, respiratory substrate. Branched chain amino acid, for example, valine, leucine, and isoleucine, can also be employed to produce acetyl CoA, a molecular circuitry that may depend on the mitochondrial deacetylase 3 that is called SID3, at least in some issues. For example, the brain, the liver, kidney, and the skeletal muscles. To this aim, branched amino acids must be first transmitted to branched chain alpha keto acids, a reaction that can be catalyzed by the cyclic enzyme branched chain amino acid transaminase CAT1. Upon import into the mitochondrial matrix where the catenate shuttle branched chain alpha keto acids are processed with a multi-step reaction comparable to the decarboxylation of pyruvate. This irreversible reaction is catalyzed by the mitochondrial branched chain alpha keto acid dehydrogenase BCKD complex, a large multi-component enzymatic system yielding NADH-acetyl-CoA and other acetyl-CoA cell esters, which can be processed by beta oxidation or the TC as end products. Of note, some mammalian cells express a mitochondrial variant of BCAT1, which is catalytically active. However, how branched chain amino acids enter the mitochondrial matrix has not been determined yet. In addition to these nearly ubiquitous metabolic circuitries, there are organ-specific pathways for mitochondrial acetyl-CoA generation. For instance, neurons can employ the ketone body to generate acetyl-CoA. Of note, it has recently been demonstrated that the acetylation pattern of the mitochondrial proteins, as controlled by SID3, is crucial for mice that respond to starvation to increase the hepatic synthesis of ketone bodies while activating bioenergetic pathways that utilize ketone bodies in extrahepatic tissues. Hepatocytes can also obtain acetyl-CoA from ethanol. In this case, ethanol is first converted into acetaldehyde in the cytosol by ADH1B. Acetaldehyde freely diffuses to the mitochondrial matrix, where it is converted into acetate by aldehyde dehydrogenase 2 family, ALDH2. Finally, ACS1 employs acetate to produce acetyl-CoA. This metabolic circuitry may explain why ethanol ingestion causes protein acetylation, preferably in hepatic mitochondria. Okay, that's all. Thank you.